In the vast and microscopic wilderness of the cell, an important event is about to unfold. Deep within the nucleus, two strands of life's most secret molecule, DNA, begin to separate. This is the beginning of replication. Our journey begins at the origin of replication, a designated site that isn't labeled by visible signs, but by an array of molecular signals. Here, the enzyme helicase arrives, a molecular predator that tears through the double helix and pries apart the strands to expose the genetic code. As the strands separate, single-stranded binding proteins come, clinging to the exposed bases to protect them from collapsing back together. Following, topoisomerase patrols the frontier, releasing the tension and preventing the strands from snapping under pressure.
If you look closely, you can see primase synthesizing short RNA primers on the strands. These provide the necessary 3' ends that DNA polymerase needs to begin replication.
Once the RNA primer is in place, transacting factors coordinate the assembly of the replisome. These factors recruit DNA polymerase III, which will synthesize the new strand. The clamp loader positions the sliding clamp around the DNA, anchoring polymerase in place and allowing it to move across the template. DNA polymerase III then moves across this strand in the 5' to 3' direction. Watch closely as the polymerase III moves across the template strand to create Ozaki fragments.
You can now watch as DNA polymerase I
comes to the frontier to fill in any missing gaps. After it removes the RNA primers, ligase will come in and fix any missing nicks in the DNA. But at the end of replication, there seems to be an error. As you can see, there is a mismatched base pair, wherein there are two purines connected together where there should be a pyrimidine and a purine.
Now mut-S slides across the DNA strands to search for mismatched base pairs. It identified the base pair mismatch. Mut-L is now recruited and shall bind to mut-S and the beta clamp. Mut-L releases mut-H, which binds to the mismatch repair and nicks it, allowing for exonuclease to come. Exonuclease is then recruited to remove the mismatched base pairs. Now DNA polymerase III is recruited to replace the missing base pairs. If you watch closely, you can observe ligase come in to repair the nicks in the DNA.